So we're going to now look at sawn lumber beams and actually do calculations for flexure, shear, deflection, bearing, and design. I'm going to split this particular lecture up quite a bit so I can walk you through the design problems. Um, and that way also you'll be, and I'll try to label these really well so that you're able to go back and walk through the design examples at whatever pace you want to. You will probably look at them a couple times, is my guess, particularly as you're doing your homework. So my suggestion is when I get into the design example, either be sure you've got uh, you can pause it if you need to, and be sure you have your supplement and code available either online or if you have a hard copy, and just pause it to look up where I am pulling values from. And that will be the best way to go through this and should make it much easier to do your homework problems. Okay, so let's get started here. Um, Go ahead and get out your NDS, so your design standard, the main one, not the supplement. So you get out the code. If you go ahead and take a look, move into chapter 3, and then in section 3.2.1, there's a couple things in chapter 3. This chapter has to do with our design piece here. So if you go to chapter 3, and we're looking at our sawn lumber, but these are just the general bending and et cetera equations. If you start out in 3.2.1, it gives you a couple facts that you need to kind of overview items that you need. One of these is that when you look at the span length, it's actually the distance from the face of the support to the face of support plus half the required bearing length at each end. Okay, so for our class, and typically it's going to be okay to use center to center of support. It's conservative, but that's okay. So they're saying you can go from the distance of the face of the support plus a half of the required bearing length at each end. So whatever the required bearing length is, you would go that far. Now, what we're going to do instead is just say center to center line of your bearing is going to be fine. Okay, so in this case, here we go. So that will be your span length L. Okay. So that in case you're wondering where numbers are coming from, that's where they're coming from. I'll either give you the span length or you can calculate it based on the bearing, the center line of bearing. Okay, notch restrictions. So in the next section, or two sections from there, 3.2.3, it talks about notches. There's only so many notches you should take out of a beam before it stops acting like kind of a typical beam and doesn't have a lot of stress raisers that cause the problems. True in any of our design practices. So it refers you in this section to different sections where you can calculate if you have bigger notches than this, but as long as you restrict to these notch sizes, not to exceed these, you can go ahead and use this flexure calculations in this section. So top and bottom notches on a rafter or joist not to exceed 1/6 of the height. Okay, and that actually is listed here for each of the kind. There's this picture is not in the manual. It just lists this out in words, but 1/6 of the height. And holes in the beam not to exceed 1/3 of the height. So 1/6 for notches and 1/3 for holes in the beam. So you can quickly see if you have too big a notch, you suddenly have not much capacity of the beam left. And this is something you'll see if you pull off ceiling panels or look at the floor, you start pulling off the coverings, in particularly older houses where someone's decided, oh, I want to go ahead and run some plumbing through there. Time and time again, in these, particularly the oldest of houses, excuse me, you'll see these big notches, and you may have to. I just had a friend, I looked at their floor the other day, and he was having to reinforce and put some more joists across because of cutouts like this. Particularly when it's in like a bathroom and you've got the weight of like a bathtub in there. This is a common problem where you'll see a lot of deflection And often if you pull up the floor, that's what you got underneath. Example picture here, another older, this one's in the roof piece, but you start getting too much depth here of these notches. That's more than a 6. It looks like a half. I don't know how high this goes up into here. And you might as well have not even used that depth of beam when you cut off half of the depth to make a notch in it for piping and things. So really this has to be done carefully, or there has to be special reinforcement pieces in here, or a doubling up or something like that. So you can refer to those parts of the code that this section takes you to, but for our class on these general ones, just this is the restriction. All right. 3.3.1 in our code, it just says actual bending stress should not exceed the adjusted bending design value. That's what we talked about in the last lecture. Demand is less than strength. Then it goes into the flexural equations, and we've talked about this, MC over I, or My over I, and we know that S equals I over Y. Remember, I is in inches to the fourth, Y is in inches. So this gives you an S value of inches to the third. So we can determine that S by using the equation. So I is BH cubed over 12. In this case, we shouldn't be using BH, we should use BD. So in most of these equations, they will call D the depth, so don't confuse that with concrete D, that's the height. And B is the width or thickness. So if I do I, it's BD cubed over 12 for a rectangle, and Y is right in the center, so that's 1/2 of D, or D over 2. The other, you'll see MC over I. C is just the same thing as Y, except for if you recall from mechanics, if we measure Y from here, C is to the extreme fiber. Okay, so Y over 2. So, I'm sorry, D over 2. So Y at D over 2 is equal to C. However you want to call these terms, doesn't matter to me, as long as you know the general bending stress formula. So to get S, I can go through the calculation, or, and you have to make sure to use those actual dimensions, right? A 2x4 is not 2 inches by 4 inches. Or you could just look them up in the table of the supplement. So in table 1B of the supplement, if you go look at that, that includes the S values for sawn lumber. Okay. And we'll come back to table 1B when we do our calculations. All right. Chapter 3.3.3 talks about the beam stability adjustment factor, C sub L. And this one just has a little more detail to it. So in this section, they've gone through how you deal with this. So if the compression edge of your beam is fully supported laterally, so if I'm looking at my beam here and it's supported so that it doesn't all along here, so that by blocks or by other beams framing, or if this is a joist, for instance, if it's framed, beams framing into these guys, that can support it, or plywood floor on top, or it can be blocked into place. And so if it's supported, it deflects the way you would expect. If it's not supported, it can get a little twist in there, and that's why we changed the C sub L factor. Our stresses that are in these tables are the yield stress, okay? So it's the part where if I'm looking at a stress strain curve, I am looking at the part where it starts to go nonlinear, the peak of the linear, and the yield stress. So those are the stresses that we are using in here. We only need to design for that yield, and we only need to design for the yield of the extreme fiber. So what's the strain diagram here? Okay, and then our stress and strain are linear, so our stress diagram also looks like this. So I am designing for these stresses at maximum compression and tension in flexure, right? All right, so where do I find this stuff and what does it look like? Well, first, here's an example of ways to support along the compression flange. So if I'm standing on here, I'm bending these beams, the top flange is in compression, bottom flange is in tension. This plywood that is put across for the flooring surface, that's what's done, is enough to brace the whole top flange. Okay. The other option would be, in this case, you see the framing members coming in here. Those are, in this case, bracing the top compression flange. Okay, so how do I find that? If it's fully braced, or if the depth is less than the width, you just use 1. Okay, there's no adjustment essentially. So when you do your equations, go ahead and multiply by 1, however many of them are 1, just so you don't forget any of the adjustment factors. The next piece says if those aren't true, then you go to 4.4.1. Oops, in the bounce that far back. Okay, 4.4.1 in the code. And it's a list in there. If you go to that pause and go to that section of the code, what you'll see is there's a list of kind of rules of thumb. They're based on practice of things that worked. If you can meet those rules of thumb, then you can also use CL equals 1. Okay, so they base it on the ratio of the height to the width and a certain amount of lateral stability. And so you want to read those to see if you qualify to just use 1. Likewise, continuously supported, it's 1. And if you don't meet the 1, then you have to use a C-sub-L that you calculate. If the unbraced length doesn't meet the requirements, it's going to be less than 1, so you're going to get a reduction because of this potential for essentially twisting or buckling. You can either calculate it using the equation in this section, so go look at that section, or you can just go to the table in that section, 3.3.3. I am not going to have you hand calculate things that are in tables, but you probably want to do it once to satisfy your curiosity that they agree. So much like if you've had steel design, there's often equations you can do, or you can just, when you're looking up the section, look at that property. It's similar here. So the tables, practitioners are going to call doing the equations an academic exercise. It's good for you to do it once or twice. But the actual calculations will typically come straight from the table so that you can keep moving on. The equations are helpful to understand where those values came from because whatever factor or whatever variables are in the equation, those are the things that are affecting it, right? So things like how far between bracing and things like that. Okay, excuse me. Some terminology stuff that you'll hear in wood. So moment applied about the strong axis. That's my normal, right? If this is my tall side that I'm bending around this axis, right? That's the strong axis. That's typically what's going to happen. Okay, it's not typically going to be about the weak axis, but of course, if I have a column that's not square, I can have that has flexure in it. I can have bending both directions, and there's some other cases where you can have that. Generally, we're going to be just bending about the strong axis. If you get involved with a lot of wood design, you'll have the manual, or you can look in the manual that your employer has, and you can go into greater depth. We're teaching you, just like all the other materials that we do, you don't touch every piece of that steel manual, and you don't touch every piece of that concrete manual or the pre-stress manual. So all of those codes and manuals, we're giving you, basically typical flexure, typical shear, typical tension and compression and deflections. For unique type structures or out of the ordinary, those pieces are in there as well, and you've learned to read these codes, and so you should be able to find if mine doesn't match, for instance, the CL value, if it doesn't match what it says, then it will send me to the place to figure out how to deal with that. All right. You will hear in wood terminology that moment applied about the strong axis could be called loaded edgewise bending, or loaded on the narrow face. By edge, they just mean this narrow face. So it's loaded edgewise, it's bending on the edgewise fibers, or it's loaded on the narrow face, when that was pretty self-explanatory. Likewise, if it's on the weak axis, it's bending about this axis, it's flatwise bending, or loaded on the wide face. Okay, so just so you know if you run across that. In this class, as in all structural documents that you'll see, the assumption's made that the load is applied on the strong axis unless otherwise noted, is what UNO means. Unless otherwise noted. Okay. Decking, and you've seen me say this several times, except for decking. Decking is a separate item that we'll cover separately. Makes sense, I guess. All right, so let's do a beam and flexure. I'm going to pause here and fire this up as a separate video so that it's easier for you to just come back and look at just the example.